Leah here from leahforsci.com/MCAT, and in this video, we're going to start our discussion on balancing redox equations. Say you're asked to balance the following equation. Ag plus aqueous plus Zn solid goes to Ag solid plus Zn2 plus aqueous. Up to this point, we've only been balancing the atoms. But if we look at this from the atomic perspective, we have 1 Ag and 1 zinc going to 1 Ag and 1 zinc. It looks balanced. But when you're dealing with redox and a change in oxidation number, it's not just the atoms that we have to balance, we also have to balance the charge. If we take the net charge on the reactant side, we have Ag plus Zn0 for a total of plus 1. Net charge on the products, Ag0 and Zn2 plus, gives us plus 2. Something's off. And this is why there's a more complicated approach for balancing redox. Now I say more complicated, but it doesn't have to be scary. If you have a checklist and a logical system to follow, so long as you can check off every item on the list, you'll know that you did it correctly and you're good to go. I don't think you're going to see anything this crazy on the MCAT. However, it is worth knowing the steps just in case you have to execute on one of the pieces. So how do we balance redox equations? First thing you do is find the oxidation number of everything in your reactant and your product. We covered oxidation numbers in detail in a previous video, which you can find on my website, leahforsci.com/reactions. But as a quick reminder, if an element is by itself, if it has a charge, that's the oxidation number. If it doesn't have a charge, the oxidation number is 0. That tells us Ag has an oxidation number of plus 1, Zn solid 0, Ag solid 0, Zn2 plus 2. The next thing you want to do is identify what gets oxidized and what gets reduced. First, I like to pair up my species. Then we'll use the trick that I taught earlier in this series, where in the case of Ag, the charge is reduced from plus 1 to 0. It goes down. It suffers a reduction. That means it's the reduction half reaction. And zinc going to zinc plus 2 goes up, or should we say op spelled with an O, tells us it is the oxidation half reaction. Once you know what's oxidized and reduced, we want to break it apart so that we can balance the half reactions before putting it back together. A word of advice. This topic gets so messy that the neater you can keep your paper, the better. I often see students doing a reaction, they have their arrow, they continue. Doing another reaction, they have their arrow, they continue. Instead, I like to put my arrows down the middle so that I can always look at the right side and identify my products, always look at the left side, identify reactants with no confusion. Let's start with the oxidation of zinc. In the reactant, we have zinc solid. Let's omit the phases to keep it simple. In the products, we have zinc 2 plus. For reduction, we have Ag plus going to Ag solid. Next, we balance the half reactions, where the order is very, very important. Start with your non-hydrogen and oxygen. Balance your oxygen by adding water. Then balance your hydrogen by adding H+. Now remember, H+ is acidic, so I'll show you how to change this in basic conditions, but I always start with adding H+ regardless. For this reaction, we have just zinc and Ag, no oxygen, no hydrogen, and these are already balanced. So we simply look at it, verify, 1 zinc on the right, 1 zinc on the left, 1 Ag on the right, 1 Ag on the left. Once the atoms are all balanced, we balance the charge by adding electrons. And this is where you want to be careful. One approach is to remember that adding electrons is reduction and removing electrons is oxidation, but I find that difficult in this context. Instead, I like to think of it from a mathematical perspective. If the only thing we can add are electrons, and electrons are negative, anytime we add an electron, the charge is going to go down. So what I want to do is compare the charges on the right and left, and whichever one is higher, that is where I'm going to add electrons to bring it down, because the electrons will make the bigger number smaller. If I add electrons to the smaller number, it'll make it even smaller, and that won't help us. Let's take a look at zinc. The net charge for the reactants are 0. Net charge for the products are plus 2. If I add electrons to 0, I make that negative, and there's no way to balance that with a plus 2. But if I add electrons to a positive number, the electron being negative will bring it down. What we want to do is make the bigger number equal the smaller number by asking how many do I need to subtract to get the smaller number? Plus 2 minus x is equal to 0. 2 minus 2 equals 0, and that means we add plus 2 electrons to the products. Same thing for reduction. Sum of the reactants, plus 1. Sum of the products, 0. How many electrons will bring plus 1 down to 0? Plus 1 minus 1 equals 0. That means I have to add plus 1 electrons to the reactants. Since redox is the transfer of electrons, the same number of electrons gained by one half reaction has to be lost by the other half reaction. If zinc is losing 2 electrons, it's giving 2 electrons away, then silver can't simply gain 1 electron, it has to gain 2 electrons, because silver is what's picking up the 2 electrons given up by zinc. So we have to make sure that the electrons in the oxidation half equal the reduction half by finding the least common multiple. In this case, if we have 2 electrons in the oxidation, we should have 2 in reduction. And to do that, we simply multiply the entire reduction half reaction by 2. I don't recommend leaving it like this. Instead, I recommend you distribute that 2 as quickly as possible so that you don't make a mistake down the line. How do we do that? Just multiply everything by 2. 2 times 1 electron, 2 electrons. 2 times 1 Ag plus is 2 Ag plus. 2 times 1 Ag solid is 2 Ag solid. Now that I have the same number of electrons, I can cancel them out, because if they're gained by one and lost by the other, they don't show up in my net or final reaction. 2 electrons in the reactants on the reduction side cancels 2 electrons in the products on the oxidation side, and I know my reaction is balanced. But we're not done yet. Next, we want to sum it up, cancel any duplicates, and check everything. You want to make sure you didn't come all this way only to find a mistake at the end. So how do we sum it up? Just like when you're doing math. Draw a line at the bottom and bring your numbers down. Again, bring that arrow down in the middle so that everything on the reactants and products are clearly separated, and this is where that middle arrow helps avoid confusion. As you're bringing it down, I recommend crossing it out so you know for sure you didn't miss anything. On the reactant side, we have 1 zinc, 2 Ag plus, and nothing else. On the product side, we have 1 zinc 2 plus and 2 Ag. Put your phases back in. A metal by itself is solid. A metal with a charge is aqueous. Cancel any duplicates, which we don't have in this case, but later you'll see water dropping out a lot. And finally, check everything. Does this look like it's balanced? 1 zinc, 1 zinc. 2 Ag, 2 Ag. Sum of the charges, 0 plus 2 times plus 1 is plus 2. 1 times plus 2 plus 0 is plus 2. We are good to go. This is a balanced reaction. Now let's take a look at something more complicated when we actually do have oxygens and hydrogens to balance, and that's exactly what we'll look at in the next video. First, give this video a thumbs up. Make sure to subscribe to my channel so that you don't miss out on any new MCAT videos. Then visit my website, leahforsyth.com/reactions, for the MCAT stoichiometry and reactions practice quiz and cheat sheet. The link again, leahforsyth.com/reactions.